I'm glad Josh talked about wind tunnels, right? When I started my graduate study, I was actually working in wind tunnels. And boy, that wind and dust and poisonous gas and so on. So I decided, what did I do? I decided to switch over to find a desk job and do the high performance computing. This is why, how I get here. Right, so talking about big data, and a lot of people talking about 3 V's, and but big data has continued to be a amorphous concept that until you really define it, what you are talking about. When big data started, my phone started ringing 24/7, and virtually the whole world, every IT person, IT company start calling. They have a big data solution. So this is really what we don't want to see. We have real problem to solve, and we wanted to define what our problem is and what our problems are, and to solve it accordingly. So I wanted to talk about the typical data issues, data problem we have. A typical data analysis and data processing workflow at NASA started with an investigator thinking of a problem, and he queries a metadata server, trying to find the data and order the data from a data center. We have a big data center, actually many of them, and the data center fulfills the order of the request. By preparing the data, typically when you order the data, you only order a subset of the data. So data center will subset, resample, average, whatever kind of magic they do. They put the data on a FTP server, and the user go there and fetch the data. FTP transmitted to their home institution, and they process the data and do their simulation. Right, that entire workload takes a long time. And talking about staging the data, they don't have a lot of time. They don't have a robust infrastructure to stage the data. So a lot of work is spent on manipulating the data, staging, and managing the data. Okay. When they have done their simulation or research, they have to put the data back into the data center. That's really, really cumbersome. And the analogy this morning showed, and Andrew showed this, I think, similar slide, a library there, right? We have a library of data, and I intentionally put a number of challenges, both from the user's point of view and also from the provider's point of view there. So that's kind of a library science people, they are studying this. And what they don't do is the next phase. How do you find that needle in the stack? What kind of software, what kind of analysis that needs to be done? So this is the traditional library science issue. So I've shown this slide before, and this is from Ian Foster of Argonne. And a typical university professor, a typical principal investigator, they have a small lab, and what they can do is limited to that kind of infrastructure. Okay, and typically it's about 50 terabytes or so, something like that. Okay, and if you wanted to do something bigger, that's not going to happen. you need to go to the data center, big data processing place. So here's some of the challenges. The investigator must have local storage and the analysis capability. When you talk about analysis capability, it's typically some kind of a robust software infrastructure, the tools that you wanted to use, okay? And that includes a lot of the hardware, software, and tools. And the local capability must be duplicated to all the PIs, every institution. So it's very, very repetitive and very costly. And I talked about the 50 terabyte of data. That's probably maximum how much you can deal with. And the investigator must also deal with local system admin and system architecture design, IT infrastructure. We heard that. Operation and maintenance, all those are good stuff that we researchers typically don't want to deal with. And also because of the dependencies to local computational environment, when you build something, you start tailored to your local environment. That entire process become very local dependent, and it's not easily portable. So you cannot exchange your workflow with other people. That's very, we talked this morning, we talked about interoperability is important. So the knowledge gained may not be easily transferable. So we know there are issues there, and NASA start trying to solve this problem. We tried a couple of different projects. I reported to a similar group here before about the NASA Earth Exchange. I will talk about that more. We are making some new progress. And also, we are working on a project called Observable MIPS. It's an observation for model intercomparison project. It's based on the Earth System Grid Federation, ESGF, and it's built on top of a Hadoop file system and using the MapReduce algorithm. We are doing a lot of the data management research, what kind of tool we need to bring in, what kind of system we wanted to build, what kind of architecture that we can manage the data and manage the data movement. Remind me that I need to talk about data movement. That's a significant issue that we have. So the functional architecture, on the left-hand side, that's the traditional data management and library science kind of function. You wanted to prepare the data, index the data, safeguard the data, and put together metadata server, providing subsetting and some simple statistical data preparation kind of functions. On the right-hand side, that's the new big data paradigm that we wanted to analyze the data with some additional tools. Okay, so we are basically building this type of architecture. So I'm getting into some specific example. So observation for model intercomparison project. Look at this chart. Those are the 100 years climate prediction data. And the shaded area, those are the model uncertainties. Any CFD model, any climate model has a number of empirical parameterizations in there. And those parameters impact your final result. And those are the uncertainties. And for the past 20 years, we have not been able to narrow that uncertainty It's a fundamental, because we are doing non-linear, dynamic problem, and any kinds of small signal will eventually grow if there's not enough damping in the system. So there are some discussion in literature talking about their limitation. And our ObservaMIPS project, the motivation is, okay, we know models are not perfect. And how do we narrow those uncertainty by bringing in additional observations? And I talked about this. Many people, modelers are not stupid, right? They use observations. They wanted to use observations at least. But because of the problem, they have to find the data first. They have to stage the data. They have to FTP and bring it to their local servers. It's just too cumbersome, so they don't do it. What we wanted to do is to provide that kind of capability, so they can use it. They don't have to go through that pain. So the IPCC, that's the international program that produced the climate assessment for the United Nations, and that's climate assessment. And on the right-hand side, that's what we are building. We bring in all the NASA data and specifically tailored and formatted and staged for their analysis use. The goal is, of course, to reduce that uncertainty and be able to use by multiple communities, climate scientists, the impact and mitigation, decision-making managers. So we build this the tools around those use scenarios. Here's a data volume comparison. CMIP3, that was in 2006. There were like 15 models produced about 35 terabytes in 2006. In CMIP5, that's just finished last year, 2012, and the data volume grew by 100 times. And right now, we are preparing the next CMIP, Climate Model Intercomparison Project, that will be done in another 5 years, and we anticipate, if not 100 times, probably tens of times. That's a conservative estimation. So how do we do that, right? And here's a document that published in Science, how much data, how the data will grow, and the blue color shows that's the observations, mostly satellite data. And the orange shows that's the model data. So we are talking about lots of data in a couple years. Okay, so why is satellite data, satellite observation important to the to Earth system models? I talked about this. We use the observation to interrogate, to limit the data, to constrain it, limit and constrain the model. And this is a summary of ObservaMIPS. Use the NASA observation for the model intercomparison project, and the IT infrastructure that we all dislike so much. We are building it, try to build it for many people to use. We started building this Earth System Grid Federation, ESGF. It's a distributed data management system that all the modeling groups are using, about more than 20 of them around the globe. So this is the type of data problem we are going to deal with. The data will be highly distributed around the globe, and lots of data. So how do we move the data? How do we compare the data? That's what we need to deal with in 5 years. The fundamental local architecture, what we're doing here is, of course, we extract the data from the DAACs, from the data archives, and we reformat, we put it in a model a format that models can use in the ESGF. So imagine you have a model run, you have certain output, and there's a data set that can be used to compare, to constrain your model that happen to be in the same format. That's what ESGF is doing. Okay, all the metadata. How do you search the data? The way you search the model data is the same as the way you search observation in this ESGF system. So that saves a lot of time for the climate scientists to search and prepare the data. This is a little bit of detail that we're talking about some of the services. Very, very important on the left-hand side, I guess. Yeah, on the left-hand side, a lot of that is metadata preparation. We enforce all the model output, all the observation data use the same metadata convention. So this way, it can be easily searchable. All right, so wanted to show some very important result. Many modelers would like to see, okay, my model is doing the best. Nobody can do a better job. A higher resolution will give you a better result. Not necessarily. When you get down to finer and finer resolution, you start to get into some of the unsteady features that you may not want it to be there, may or may not. Model simulation is one realization of the observation. Okay, so in this case, from the observation, we define the observation uncertainties, and all those scattered points are from different model results. So they are all over the place. Many of them are outside of the observation uncertainty. That means the model are not correct. And on the right-hand side, the climate modelers are developing the metrics to measure each one of the model. This is the spatial distribution, a similar kind of concept, but a more complex plot. I won't get into it in detail. So here's a post-CMIP-5 challenge. So we publish the result, and once we show the models that are outside of that gray box, there are a couple of modeling centers took a look and say, oh boy, my model is not doing the right thing. They start, getting into their model and changing it. They quickly come back into the gray box. That's within 3 months of publishing the result. Okay, so that's how powerful this data management system is. Once you have that in place, you can do it. You can rerun your model and compare to observation and do it very, very quickly, and you can get it done in 3 months. So what have we learned? Model output has systematic arrows, which is a linear combination of large-scale arrows, parameterization, and covariation arrows. And in order to do that, at least three, to reduce that error, at least 3 modeling centers that they were able to correct the system error and bring them back into the tolerable, to agree with the observation. And satellite data, of course, can be used to constrain the model. And large-scale data management infrastructure, such as ESGF, is critical, is necessary to make the model intercomparison project relatively painless. So this is something that, and because of the rapid growth in model output, the future data infrastructure will have to be, will have to minimize the movement of data. That's how the stored data, the compute will need to be closer to the data, and that's the last bullet there. I also wanted to talk about NEX. The vision is to basically provide a science as a service to the earth science community. We have a user community, a network, social network kind of infrastructure for people to play, to use. And then there's a development platform, that's the sandbox. We put in a lot of the data model and hardware, software infrastructure. Hardware is here, and data, tools. So that's how if you put all of them together, that's a very, very powerful system that people can use. And I talked about data importance of data management, the tools. Of course, we have all the models, and the compute. We're building this compute interface to interface with HPC and cloud and so on. Okay, so the users interact with this whole system through direct interaction, or interactions, or through workflow. Some of the examples. This is 20 years, 30 years of Landsat data. It was never done before. Now we can process 20 years of data very quickly in a matter of hours, and to find a trend, to find signatures. 2-3 weeks ago, we just published another paper using this infrastructure, because we find out the forests are moving to the north, about 200-300 miles. Okay, the vegetations are growing in Arctics, and that's being observed. But in the past, we weren't able to process the data to understand it, and now we can. That's really how powerful this platform is. And also, once you have put the data together, let me go back one slide. For example, this one, Landsat data, you don't see India in this plot because of the permanent kind of cloud cover. But you can use some other proxy, in this case, precipitation. So you can see through the cloud and understand what's happening on the ground. So you can use some other data sets to complement your existing data set. Or you can go into finer and finer detail. The Landsat data, you can have different resolution. You can bring in higher resolution. And then you can go down to the plot scale data. So it's if you don't have this kind of infrastructure, you will never be able to do this. And this chart shows the high resolution national climate assessment data. We are using, bringing in 35 global model results and use the statistical downscaling method to get down to the high resolution model data. So we are making this data set available to the user community. And guess what? They don't want to bring it down to their local analysis environment because itself, this data set itself is 40 terabytes, and they don't want to move the data. They are doing the analysis on our platform. We are also supporting the climate monitoring system, carbon monitoring system, using the multiple sensors, multiple satellite data platforms. So, as a summary, challenges, we have a software development practice issue. Earth system scientists are not trained with software engineering. The codes are very poorly organized and structured. Computational scientists are often not trained with Earth system science, so they that results in very poorly executed code and significant model error. I'm not saying computer scientists are not doing the right thing. A lot of time is lost in translation. Domain scientists wanted to do something, but it was coded incorrectly or some that kind of issue. I had an experience that we parallelized a code, spent $2 million, and the domain scientists couldn't understand the code. They threw the code away. The result wasn't it was not validated very well. Validation and verification model needs to be validated with observation, models and observation are producing tremendous amount of data at different time and spatial scale, and it's a significant challenge to compare the two. We need to develop the tool and environment so the productivity, we can increase the productivity. We need to develop our workforce. We need to do the short-term intensive education. Our conclusion is we need to educate the domain scientists with software engineering and high-performance computing. Last summer I brought in a bunch of PhD students at very good MIT, Columbia, very highly regarded university. And the student came in, they have no idea about parallel processing. They're still, their mind of data analysis is a plot level, at a theme level. They don't even know if they process. This is an embarrassingly parallel problem, right? Process the entire globe of data. It can be done, but they had no idea because of the lack of knowledge of parallel processing. Our computing and modeling centers are looking for interns to work with our problems. We are building up the workforce. That's all.